about the so-called, in the form of linear SVM. And we say we're going to build a linear classifier with this weights W, and then we have the bias B, and we separate them. So we have W and B. We want to learn these two sets of parameters here. The decision boundary is linear, right, in this case here. And then we say that in the dual form, so it's important here, in the dual form of the linear SVM looks something like this. So in that case, the variable we're trying to optimize is this Lagrangian multiplier alpha here. So there's one alpha sub I for each data sample. So overall, you have m number of alpha here because you have one Lagrangian multiplier for each data sample, because that corresponds to one constraint you want to satisfy. You want to be correctly classified. And then the objective function becomes this kind of quadratic function in terms of this Lagrangian multiplier alpha here. If you look at them here, so this is the linear term of the Lagrangian multiplier, and this is the quadratic forms here. So even though there are a lot of terms here, but then let's think about it here. So y I and yj here, those are labels. Could be +1 or -1. This is the x here. This is the input data here, xi and xj here. This represents the inner product between these two data samples here. Essentially saying this, right, is a quadratic forms of alpha sub I, alpha sub j here. The coefficients of this quadratic alpha sub I, alpha sub j here depends on the product between the target labels and the inner product of these two x vectors here. But however, in the end, this will give you numbers here, a scalar number. And this will be the coefficients in front of these quadratic terms here. So overall, you can think that even though we have a lot of variables written in this form, in the end, this overall function is simply a quadratic function of this alpha here. So alpha is a Lagrangian multiplier. And then we're trying to maximize these quadratic functions here with respect to alpha here, subject to constraint alpha to be a non-negative and upper bounded by this regularization parameter alpha here. And then another constraint that's summations of this stuff here has to be equal to 0. So that's the kind of dual forms of the linear SVM we talked about last time here. And if you know how to solve this problem here, and then in the end you solve the Lagrangian multiplier. If you know the Lagrangian multiplier and you know the solutions of the W, you remember that W is simply equal to summations of alpha I and xi here. And we say that many of this alpha sub I are exactly 0. Only those along the boundaries or misclassified data points have non-zero alpha sub I. And we call those data points corresponding to non-zero values. We call them support vectors. We call those data points support vectors. So a benefit of this SVM framework is that only a subset of data samples are support vectors. And in many actual applications, majority of data samples are not support vectors because they are in interior of the decision boundaries there. So in that case, only those located along the boundaries are support vectors. For instance, in these examples here, only have 3 support vectors in this case. Okay, so these guys here, if you look at this form here more closely, and then what matters to x input vectors here, those feature vectors here, only matters is the inner product between them here. And that's it. It doesn't involve anything else. Only thing involved is the inner product between these two vectors here. So essentially the dot product between xi and x sub j here, and then let's say we define them to be in the k sub ij, to be the inner product between the I sample and j samples. It somewhat measures the similarity between these two samples. And how similar they are. If they are very similar, and you can imagine if xi, xj has been properly normalized, and then the inner part simply is this angle between them, right? So if they are completely aligned with each other, they have maximal values. If they are orthogonal, and then the k sub ij is 0. So it's somewhat k sub ij measures the similarity between the two data samples. So in the end, in this quadratic forms here, in the dual optimization forms here, and then what matters only is you have a metric to measure similarity between the two data samples here. And that looks like that's the only thing matters. It doesn't involve any other forms of x. The only thing involves this x here is it measures the similarity in terms of the dot product between different samples here. So this is the interesting observation. We will explore that in the next slides. All right, so the question is this. So this is a linear SVM. And we said that how do we generalize to be a nonlinear decision boundaries? And in that case, what we say, one way we can do is to introduce new features. For instance, you can use quadratic features. You can use polynomial features. You can use even other more complex forms of the features. And for instance, this is the example we given previously. Suppose you want to do a binary classification with one-dimensional data sets here. You have these red dots and blue dots surrounded by blue dots here. Of course, a linear classifier cannot separate these two guys here. However, if we introduce one more features to be the x squared, to be the quadratic features, now in these two-dimensional features here, you can draw a line to separate these two group of data points here. So in that is very helpful. In many cases here, you can introduce this kind of a high order features and then build a nonlinear decision boundaries. So let's look at it here. Suppose, let's take these examples here. And we say we want to expand the feature from original x here to be more complex forms, to augment them with another set of features. So for instance, suppose initially you have set of features x1 to be x1, x2, and x sub n here. Suppose let's expand that features to include additional polynomial features up to order n here. And then we call that my new set of features. So which means that given the x here, I will calculate a constant term to be the linear term, original terms here, x1, x2. And then now I'm going to calculate the quadratic terms, x1 squared, x2 squared, and then maybe the interaction between the two features here, x1 times x2, x1 times x3, and so on. So now you introduce a lot of higher order terms into the features. Suppose I collectively call this augmented features. I call it to be phi here. I say phi is a new feature vector, much bigger feature vector here, but it is generated from my original x here, and then call that as the new feature vectors here. So right now, I generate them using quadratic features here, up to order 2 here. So I can generate all those features here to be my new phi here. And now based on this new feature here, and then I can define a new linear classifier, but now it's based on this new features here. And then I have a new set of W and a B here to learn. The W, of course, that is going to have a more parameter than the original ones here, because W now depends on how many features in this new phi here. What's the dimensions of phi instead of dimensions of x? So in general, that's a big numbers for that. But again, once you augmented the features here, and then we apply the exactly same framework of SVM to learn the W, to learn the B. And that's similar like what we did before. So now let's look at here. Let's suppose now we have the new features here. Now I look at the SVM dual forms of the SVM optimization. And what does it look like? Well, it looks like something like this. So instead of the dot product between this original xi, xj here, so now I have the dot product between phi xi and phi xj here. And that's the only place that you will make any changes. All the other places stay the same. So that's kind of interesting observations here. So in this dual forms of this SVM optimization, based on this new feature phi here, all rest of the things stay the same. The only thing changed here is this kind of an inner product. Instead of inner product between xi and xj, now I have the inner product between phi xi and phi xj, and that's it. That's it. So, so for instance, in this case here, and how do we calculate phi x and phi dot product between these new feature vectors here? And suppose this is the x, suppose this is the phi x here, this is the augmented set of features. So now you plug in two vectors here, one is a and a b here, you calculate them. So now you calculate the inner product between these two here. So, so right now I use slightly different notations here. In slides, I think the notation here again, because the phi here is viewed as a row vector. So that's the reason I have a transpose here. But you can think about just the dot product between these two vectors here. So if you take dot product between these two vectors here, and then essentially take component-wise product and sum them up, and then what do you get have in these forms here? Looks like a very complicated form, right? So you have this AI bi here, these terms here, and then you have new terms here. It essentially involves all the pairwise product and then put them together here. However, in the end, you can combine all this. It turned out in the end, the form is very simple. It simply is this polynomial functions here to be a 1 plus ai bi here, and product between the inner product between the original vectors here, take the square of that. And you can verify that that's indeed the dot product between these new vectors here. In fact, and then some of you may wonder why I put all this coefficient in this particular form here. The reason I use this particular coefficient in such a way that in the end, I will be able to when I take a dot product between these two here, I will be rewriting them in the simple forms there. So that's interesting. Let's pause here. Let's see what they mean here. So this is what they mean in this. So what matters to us in this dual SVM form is to calculate the dot product between two pairs of samples. And what happens there in the two pairs of samples here, in the end, what matters here is this functional forms of this k functions here. That is k, the functions of a and b here. A and b are original vectors here, not augmented features, but original features here. As long as if I using this quadratic features in the polynomial forms here, in the end, in order to calculate the dot product, I have a much simpler way to calculate them. It's simply plugging AB into this quadratic function here, and now I'll be able to calculate the inner product between these two augmented features. So that's kind of interesting. So which means you do not need to keep track of all the features here. Instead, I can simply use this function to calculate this inner product between these augmented features here. So that is the key message, came from this part of that. And these guys here, this function here is a function of k here, take two variables, two arguments. One is this, one is a, and both a and b are original features. Essentially saying this, the augmented dot product between augmented features here can be simply write down as the functions of k, a, and b here. Of course, here is a quadratic function, polynomial function up to order 2 here. This k here has a specific name. It's called a kernel. It's a kernel here. So there are a specific type of kernel called a Mercer kernels. So for Mercer kernels here, imagine now you have a functions k here, and you have two variables here, x and x prime. So they are same dimensions here. If this function is called a Mercer kernel, if it satisfies these conditions. And this condition is saying this, if you take any functions g and a here, and then plug in any function b here, now you integrate over this kernel function here, they're always non-negative. If that is the case, this type of kernel is called a Mercer kernel. So this Mercer kernel is a generalization of the concept of this matrix concept of positive semi-definite. So in the case of, if you remember that when we said a matrix is positive semi-definite, if, let's say a matrix A is positive semi-definite, if this take any vectors here, take a vector of x transpose A times x is always non-negative. In that case, it's called a positive semi-definite. So this kind of Mercer kernel here is a generalization of this matrix concept. However, the reason we cannot use matrix here because this function k here is a continuous functions of x and x prime here. So unlike in the case of the matrix, you only have a fixed number of rows, fixed number of columns. So you can think about is a infinite extensions of these matrix versions of the positive semi-definite here. So if this condition is satisfied, we call it the Mercer kernel here. And then there is a proof, there is a theorem saying that, in mathematics saying that, if k is a Mercer kernel, then there exists a certain feature extension such that the Mercer kernel k and b can be written down as the inner product between these two extended feature sets here. And that means this. If I have, instead of identify the feature vector, extended feature vectors first, and then calculate the inner product between them, I can do the reverse way. Reverse way is this. I'm going to identify a kernel first. Then I try to identify the corresponding augmented feature vectors augmented features here, and then I can calculate inner product between them. Now, however, so in our case, in the case of SVM, in fact, we do not need to do this because this individual feature vector did not appear within the dual forms of the SVM. The only thing matters is this K kernel functions here. In fact, we do not need to know what are the augmented feature vectors for my X here. In fact, it doesn't really matter. So this is one case it doesn't really matter. In some other cases here, in fact, this feature vectors here can have infinite dimension. So in that case, you cannot even write down them here. So more conveniently, we might just work with this kernel directly instead of working with the extended features. So that is in general, what we're going to do when we use the kernel versions of the SVM. Just need to identify a kernel function for that. All right, so in general, this phi here is sometimes you cannot identify them. It's very hard to calculate, right? So it's much easier to just write down a kernel function here. So that's the only thing matters here, easy to compute here. So there are some common choices of kernel functions here. I list a few of them here. So the first one is the ones we just mentioned here is polynomial kernels here. Given these two feature vectors here, A and B here, that is this polynomial functions of A and B here up to order D here. Or look in the functional form will look something like this when X have one dimensions here. So when A and B have one dimension, you can plot this kernel function look like something like this if D equal to 3. So remember that kernel give you the concept to measure the similarity between these two data points. So in this case here, it's saying this: when these two data sets are along the same direction, when A and B are along the same direction, they have a higher similarity than those things in the opposite direction. If they are in the opposite direction, this is the inner product between the A and B, they will be negative. So they have a lower values than those on the same direction. However, this similarity is somewhat unbounded for these polynomial kernels. So as long as B is a multiple of A, and with different positive multipliers, the higher the multiplier, the similarity they are. So you can kind of unbound it in that case. So this is so-called a polynomial kernel. For polynomial kernels, you can write down these corresponding phi functions, the corresponding augmented features. So they are simply the polynomial terms of this A functions. So another very common popular choice of the kernel function is the so-called radial basis function. So radial basis function looks something like this one here. So, and you already encountered, it's very familiar to you. It looks like a normal distributions, right? So like the normal distributions have a high value in the center. When A and B are exactly the same, they have a highest similarity, and then decays when A and B are away from each other in terms of Euclidean distance of that. So this is so-called a radial basis function. This is probably one of the most commonly used kernel within this SVM framework. And this parameter sigma here, and that, different sigma lead to different basis function here. And so that sigma here to give you some metric of how confident is this measures the similarity here. If your data is highly, very densely populated, in that case, you may use a smaller sigma. So in that case, I'm gonna look at the data immediately surrounding my data points here, and then I don't need to consider data further away from that. However, in the case you do not have many data sets here, you might want to use a relatively large sigma here, such that when you do classification, you consider not only this data next to them, but slightly away from that. So that sigma sometimes is a hyperparameter you have to choose in actual applications. So this third one is this kind of hyperbolic tangent function. So this is saturating sigmoid type functions here is a kernel here. So in this case here, it's saturated on both sides of that. So they are, when those X are along the same directions, so they have relatively high similarity, high kernel values, inner product values between them. However, it saturates, which means that as long as they're same direction, after a certain range, they are always to be 1 here. So in the opposite direction, they are lower bounded by -1 on the other side of that. So this is called hyperbolic tangent. This is a saturating kernel function. So these are the common choices of kernel functions. All right. So however, as I mentioned that only when a kernel is a Mercer kernel satisfied the condition I just talked about. In that case, there is this definitions of this phi vectors here, and then which means that there is underlying notions of the inner product between these augmented feature vectors. But in many cases, in practice, and people often choose kernels, they're not in Mercer kernels. So they may calculate, identify a function here, give you a concept of similarity, but that similarity, you cannot come up with the underlying feature vectors that can be understood as the dot product between the underlying augmented inner product between two augmented feature vectors. So that's very common as well. So in fact, in practice, in many of the real applications, and then one of the challenges is to choose what kernel to use for specific application, or maybe you come out with newer kernels for your specific applications. So this is very commonly used in many application in the text or string applications. And for instance, if you have a text here, or let's say for biology application, you have a sequence of DNA sequences. How do you measure similarity between two sets of DNA sequences? And that would be an alphabet of ACGTs. So in that case, and people came up with a similarity to measure the strings between two sets of strings. And then as long as you came up with this called string kernels, and then you have that, you can use it for classification problem. That's very widely used as well. So, so they may not be a Mercer kernel. So, but however, it looks like it doesn't really matter that much. All right, so once you have this SVM framework here, what does the decision boundary will look like? So have you thought about that? So decision boundary here, so I don't have it here. Let me go here. Let me show you what's the decision boundary. So decision boundary in the end is the dot product between your data samples and your new data here. Okay, so that's the similarity you want to measure here. So in the end, it turns out the predictions here simply depends on the kernel function itself. Doesn't it really depends on this the augmented features. So so what I mean here is this. Let me write down that so make sure you understand what's going on here. I'm going to switch the screen here just to make that point here. I'm going to stop sharing and I'm going to new sharing with my iPad here. Right, so what have we talked about so far in this for the SVM framework? If you remember that, was SVM framework. And what is my W? Do you remember that? W is what? W is equal to summations of I equal to 1 to m, alpha I and xi here. You remember that. So that's the W I learned from my SVM. So which means if I know the Lagrangian multiplier here, alpha I, and then I will be able to know my W. And then keep in mind that only a few of them here are zeros. So only a few of these guys are zeros here. And those are called the corresponding data are called support vectors. So not all of them. So in fact, even though it's summation over 1 to m here, only involve a small number of samples in this W here. So once you learn the W here, and then the prediction is done this. Prediction is done like this. So the y hat here need to involve the calculate inner product between x, w, and x here, plus b. So that's my linear classifier. But now if you plug in the w here, so that involves I here and alpha I here to be xi, and then the x here plus b. So you involve the dot product between the two vectors. So that's what we have for the linear SVM. So now, if I generalize these guys here to using augmented features, now this will be the kernel between x and x sub I here. So that will be the kernel versions of these inner product between two vectors. So as a result, my predictive functions here, so kernel versions of my predict here is simply is going to be a function of form to be y hat here, with the input x here, to be the summations of I equal to 1 to m, alpha I here, to be have this kernel function to the x and xi plus b. So that is my decision boundary. If this is positive, you say there's one label. If this is negative, that will be another label here. But the key thing you notice here it is. So now the decision boundary involves the kernel functions of the x here. So as a result, the decision boundary does not need to be linear anymore. In fact, that is the reason that in the end, we have choose the SVM here because we want to have this nonlinear decision boundaries. So this shows you one example of the nonlinear decision boundary for the kernel SVM here. You can see now, if I use this kind of, use this as a, in this case here, it's a radial basis functioning as a kernel here. And you can see these are the decision boundary between these two sets of data points here. This is one of them here. This is another point here. So now you have this kind of smooth version, nonlinear decision boundary between these two group of data points. And again, those things located within the boundaries are the support vectors here. So in general, in many cases, in real situation, you might get many support vectors, even though in this framework we say that. So in this case here, we say that only some of them here are going to be only a subset of alpha here are strictly positive. So in this case here, and only those positive values involved in the calculations of the decision boundary. There are many of them are exactly 0, and those ones are not involved. So this corresponding the data point here corresponding to the support vectors. So for once you generate the nonlinear model, in many cases, it's possible that you have many support vectors. So that makes things slightly more complicated. All right, so that's what I say regarding the kernel SVM here. So let's summarize what we talked about so far. So linear SVM involves this W and the B here. Overall, you have n plus 1 parameters for the linear SVM. So in the linear SVM here, we're representing them, we can represent those models here using two ways. So either represent them using those parameters here. So essentially, you store the final values of W and B, or you represent those W and B here using the support vectors here. Because you can say, well, if I only have two support vectors here, I just memorize these two support vectors. In the end, I can recalculate W and B directly from these kind of support vectors. So you can, that are two ways to represent the learned models, either using W and B or using support vectors. So they're equivalent. So in the kernelized versions, and what essentially we say, underlying theory said we are dealing with the augmented features, phi x here, instead of x feature itself, from augmented set of features, higher dimensions of that. So in this case here, it's impossible to calculate W and B directly, because W and B, and in order to calculate W and B, you need to know the phi here. However, in many cases, as I mentioned, that the phi is not clear what the phi are, what they are for some kernels. So in that case, the only way to memorize the models is using instance-based. Essentially, just memorize those support vectors here. Save the data instead of the parameters, because parameter WB, in fact, you cannot write down them here. As you can see, what I see in this case is here. If you go back to the models I have shown you here. So in this case, W and B corresponding to these guys here. W corresponding to weighted combinations of the support vectors with the weight specified by the alpha here. But in some cases here, in the kernel version, we do not know exactly what is my phi. If you do not know that, you cannot calculate W explicitly. So a much better way, just memorize the data points. And then I know how to calculate the kernels. In the end, I know how to calculate decision boundary. So that's the only way to do that. Just keep in mind that when in the kernel versions of SVM, there's no W and B because you don't know them explicitly. So, so the difference between them here, the linear SVM, you can solve linear SVM either by solving the primal versions, which means that you identify W and B directly, or by solving the dual version, which means you learn the alpha sub I values. That would be two equivalent ways for doing that. So however, in the kernel versions here, the only way you can solve the problem is through through the dual versions. That's the only way. In the primal version, you cannot, most of the time, you cannot write down them here. So that's the only way you're doing that. So you can see now why we introduce these dual forms of this of the linear SVM is that if we want to extend them to a nonlinear decision boundaries by using kernel function, the only way we can solve the problem is working on the dual space instead of the primal space. And so just keeping that in mind of that. So that's the kernel SVM. So in fact, this kernel idea has been generalized to many different types of other applications. So and just some history here before this modern era of the deep learning. So now many of the models are built based on neural networks. So before that, so the kernel methodology is more or less the mainstream of this machine learning methodology, and one of the mainstreams. And many people are spend a lot of effort try to develop a kernel-based models to solving classification or regression problem. And you can see why people are doing that. Well, one thing you can look at the functions that in the kernel SVM. One thing you notice that the optimization problem the kernel SVM is trying to solve is a so-called a convex problem. So which means the problem is guaranteed to have solutions if you have optimization methodology. There's no issues of local optimality. And that's kind of very assuring if you apply this methodology here, because which means that you will get the same solution no matter who applied this method. How do you run the algorithm? Because there's only one solution that is globally optimal. So that's the main benefit of SVM. Of course, SVM has very good theoretical foundations, right? Because try to maximize the margin. So you have hopefully you have a kind of better generalization ability. And thirdly, there's connection between the SVC dimensions of the linear SVM. And in fact, you know that people identify that the VC dimensions of the linear SVM is closely related to how big is the margin. So the higher the margin, the lower the VC dimension, and which means that the lower complexity of the model, which means that your model will generalize well on the test data sets. So there is this relationship between this VC dimension and then the margin magnitude, the margins of that. So that's all good of the theoretical foundations of the linear SVM framework. And because the SV is so useful, many people have been thinking about generalize this kernel idea to many other different types of applications. For instance, you can generalize this to a linear regression problem. So there's a version of the linear regression framework for the kernel models here. And so the way you think about it is this. So in the linear regression models here, and you remember that in the linear regression, so we have models here. The prediction here is equal to theta dot x here. So that's my linear regression model. And I want to compare the difference between my targeted value y and the actual values of the predictions here. And if you have a training data set here, and you have data set to be a data matrix to be x here, to be x1 here, x2 here, and an xm here. So your data matrix looks something like this. And we say that x theta here, so that is the all predicted values for all the samples. And if you minus this y here, and take the normal that, and you minimize these guys here with respect to theta. And you identify optimal parameters of the linear regression models. And then then you add some regularization parameters here, say you want to make the parameter to be relatively small, and that will be the L2 non-regularized linear regression framework, and we talk about it. written in this form. And we say that the solution to this problem here, it can be written down as a form of the normal equations. So that is written in this way, x theta minus written in this way. Let's do here. In terms of normal equations. So that's written in x here plus alpha identity matrix times theta equal to x transpose y. And that is the normal equation. You remember that we can use to identify the optimal parameters of the theta here. So and then solution, that's what you learned previously. So now you can think about it, extend this to a kernel models. The way we think about how to generalize linear regression to a kernel linear regression. So that in that case, we can predict the values using nonlinear functions instead of the linear models here. How do we do that? Well, you can think about this. How do I generalize the concept, the inner product here? And in fact, be able to generalize that to a different forms, and then I'll be able to derive a kernel regression to solve the problem there. So the way you're doing this, one is this. So now in this case here, if you look at this alpha theta here, and you can rewrite them, say, well, you can rewrite theta here to be alpha theta here equal to x transpose, and then x theta minus y. So you rewrite down this normal equation in this forms. Okay, so now you have these two different forms here. Let's rewrite them to here. Let's say, what is my theta here? It's simply equal to x transpose times x theta minus y divided by this parameter alpha here. And let's treat this guys here to be, define this to be a new guys here called my residual. Suppose I define my residual R to be x theta minus y divided by constant alpha. And this is residual because this is simply the difference between prediction and the target values. X theta is the prediction and y is the target value. So the difference between them here. Essentially, it's just saying here it is. This parameter here is simply x transpose times the residuals of that. So more specific, you can rewrite them to be summations of all the residuals, 1 to m here, alpha I, and x sub I here. And if you look at these forms here, it's very similar to the form we written down from the linear SVM framework. And this alpha sub I here plays roles like alpha sub I. So here is a residual. In the SVM, that's the Lagrangian multiplier, and that looks very similar. The question is, how do we kind of reformulate the problem and try to identify the parameter of the residual here instead of theta? What the way you can do here is this. So from here, you know that the theta is equal to x transpose r, and now we know here the if I do plug in the original forms here, and I know that r is equal to alpha I equal to x theta minus y. I know this guy here. So which means this, if I do, which means here, I can combine this two here, derive a set of functions of the r only here. The r only. You can do that by doing something like this. You can rewrite the function to be x transpose, and then minus alpha r here, minus alpha identity matrix times r, now equal to y here. You can reformulate the function in this form. If you're doing that, you can construct this so-called the kernel versions of the linear regression here. Let me go back, show you what this looks like here. So you're doing that, you will find that in the end, you want to solve the residual here. It's simply, you can rewrite the residual simply this again to get this dot product between these two feature vectors here. And this is this kind of a so-called gram matrix we talk about, right? This is essentially the inner product between any two set of features we have, original features you have. And that is the K matrix we have. So the residual here within the linear regression framework is simply equal to K plus alpha I inverse of that times Y. But now you think about this, right? And then the linear predictions here is this dot product between Y and X here. And now you can simply rewrite it in this form here, as I show you that, to be because this is a theta here to be simply the summation of R times Xj here. But now you take dot product between these two, and this is the predictions here. But now this becomes interesting because this is interesting because now the predicted values of this Y here and involve this K here. Originally, this is simply the inner product between X and each individual data sum Xj here. So overall, it's a linear function. But now you can use the same trick we have used for the SVM framework. We can define a new set of kernel functions. Once you have this kernel functions here, and then linear regression framework, this predicted value become nonlinear predictions. So by doing that, you can have all varies from nonlinear prediction here. So this show you one of the examples of that. So suppose this is a classical regression problem we showed you previously. You fit a line here, but now if you use radial basis kernels here, and now you can have this nonlinear predicted values of the Y here. So by doing that, you can generalize a regression from linear regression to arbitrary nonlinear regressions of that. A benefit of this methodology here is this: you do not need to explicitly specify this type of features as we did previously. Previously, we said that, well, you can generalize linear regression to nonlinear predict functions by introduce features, but you have to explicitly express those features, either using polynomial function and you choose the order as polynomial. But now by doing this ones here, you only need to choose the types of the kernels. Now you get nonlinear decision bound of that. So that's kind of way you can go beyond from linear model to nonlinear model by using this kind of kernel tricks. And again, just like in the SVM, people spend years, spend efforts here, try to identify the right kernel for each specific problems here. And then in that case, can hopefully improve the performance. All right, so let's summarize what I talked about so far. What I talked about so far is this kind of newer version of the model for so-called supportive action machines. So within the supportive action machines here, we use this idea of the margins, and we want to maximize the margins. We want to identify the decision boundary that maximizes the separation between these two group of data points of that. And we formulate the problem in two ways. In the primal way, we maximize the margin subject to linear constraints. And we can reformulate that using this Lagrangian multiplier methodology to be a dual form. So in that case, in the dual form, what we do is we optimize this Lagrangian multiplier subject to constraints. And the number of variables involved is different. In the primal form, the number of variables are those W and B. Essentially, they involve n plus one number of parameters. But in the dual form, we involve this m number of variables. M is the number of samples. So essentially, is whether you're dealing with the number of features or number of samples. So that separate into either primal or dual problem. And we also introduce the idea of the soft margin to deal with the case of non-separable case. So even if your data is linear separable, sometimes it's also good to introduce those kind of soft margins of that. And now you have kernel to generalize from linear to nonlinear decision boundary. So this is what I want to say regarding this SVM framework. And then there's a whole body of work talks about the kernel methodology or kernel tricks for generalizing most of the linear models to nonlinear models. You can always use these kernel tricks to generalize that. So a lot of methods have been developed, but I just want to give you a flavor in terms of the classification and the linear regression framework I talk about here, but there are many other places you can use it as well. So that's what I want to say regarding the SVM